Welcome everybody to today's seminar. Today's speaker is Giovanni Petri, and he will talk to us about renormalization and higher order interactions, bridging structure and dynamics in complex systems. Please take it away.
Thank you very much. Thank you for the invitation first and for this opportunity. Let me tell you that I am not really very often talking to, let's say, mathematicians in the sense of mathematical seminars, but I think this is going to be fun. And the aim here is to actually try and see whether I can convince any of you to come work on this with us, which are more, let's say, on the physics side. So there are a bunch of words in my title: renormalization, higher interactions, and I hope they're gonna mean, they're gonna make sense by the time we end this talk. And I think I hope I can convince you why we should be talking about this more. So when we talk about higher order interactions, what do we mean? Well, we know about interactions, which are usually, we think about them in a pairwise fashion. So a node interacting with another node, a neuron firing to another neuron. But in many cases, we actually think about more complex interactions. For example, another unit in the system that touches or interacts modulates the interactions between the previous two nodes, or something that is a global, like a many-body, a polyadic interaction. Now, what are examples of systems of this type? Well, for example, in ecological systems, in ecosystems, we do know that there are interactions. For example, the trees give cover to the population of mice from the eagles. They don't really interact directly with the eagles, and that is a modulation in that sense. And so you can make similar arguments, for example, at the level of neural circuits, also as you go progressively higher and higher in, let's say, in a hierarchy of sort of neural interactions all the way to cortical interactions, functional interactions in that case. And of course, as well, you can actually think about social interactions, which is another example in which we do know from many years of sociology that if three people are in a room, the decision that comes out is typically different from having the three pairwise interactions, even in a short time. Now, how do we represent these things typically? Well, basically, given the success of network science over the last 20 years, the temptation would be to use networks, which are great because, you can do many, many things with them. We have graph theory, we have statistical mechanics that works very well, but they have a limited description capacity because you cannot really code into them the fact that you have a genuine group interaction. Then if you want, in this hierarchy of complexity, you can go to simplicial complexes, which are actually very good because they solve this problem. You can code inside all the interaction of every order that you want. You also have access to algebraic topological tools, very powerful tools, but they're rigid because they don't allow you to, for example, not have a triangle if you have a tetrahedron, and so on and on. And as you progress up, you can think about hybrid graphs, which are the most general object. Which is beautiful in this sense, but at the same time, it also means that being so general, it becomes more complicated sometimes to decide what you're really looking at. What is the right Laplacian to use in a hypergraph depends very much on the application or even in how you represent the data that you have. Now, these ideas about polyadic or higher interactions are not new. I mean, even if you can go back to 1987 for spin systems where you have, interactions in many bodies, even though the setup was different. Typically, what we think about today are not systems in which you have a conserved quantity, so no Hamiltonian, and we focus more on the complexity of the interaction pattern. But these ideas are not new. I mean, even sociology, they go even further back. What you do see in papers nowadays is something that looks more like this in terms of dynamical systems, when you write down these interactions between 3-body and 4-body and so on. Now, why am I showing this to you? Well, because in a sense, why we're talking about topology in this field? Well, because, topology, at least, especially topological data analysis, on top of the low order descriptions of nodes, edges, and so on, they give you access to a more powerful language, which is, the one of simplicial complexes that we're mentioning above. And why is that related to this higher order description? Because by definition, the bricks that you're using to write down your system are interactions, if you would say, or at least are sets of different points, which typically we interpret as groups of, for example, neurons or groups of animals that are interacting. Now, something that I would like to sort of put up there is that there is a whole other part of the world that actually thinks about very similar problems from an information theoretical point of view. You must have seen this type, right? In which you have a distribution of joint variables overall. And all of these are, let's say, intrinsically higher order in this sense. Intrinsically, they describe polyadic interactions. What, at least from the topological description, you can take out is something else, right? Something that I would call, with a slight abuse of notation, intrinsically non-local, right? To have your cycle within your simplicial complex, you actually need the coordination of a bunch of edges that fill up that are closed in a certain way that gives you a homological cycle in this case, rather than just like a cycle in a graph that, for example, could be clicked out and so on. Okay, so there is some power there that is not, it's encoded also in the statistical description, but it's not as evident, right? And now there is a tension in the literature between, as far as I'm concerned, at least between the interpretation from the topological, statistical, informational level, and we haven't really bridged between them. And I think we're going to say a little bit about that today. Talking about today, why are higher order interactions funky again? You know, since I told you that we have been talking about this since at least the 80s. The way you do it is typically you look at reviews. How many reviews are out there or perspectives are coming out? That's a good proxy of what is cool. And if you look at the recent ones, they really use this language that I'm using, you know, models, dynamical models, complex systems, higher order, and so on. But really, if you go back, you basically end up looking at what were the first, or at least the famous reviews in topological data analysis. And historically, what happened, at least the way I usually tell this story and I understand this story, is that people started looking at new ways of using algebraic topology to describe complex systems, and then they started asking, well, what if instead of only fitting data, we can actually take seriously what the language we're using. So there is an actual interaction between three bodies and so on, and what are the consequences of these? And in this sense, you can think that there are effectively, let's say, two flavors of these kind of higher order approaches. One, which is from higher order phenomena to mechanisms. So I start from data and I try to figure out what's going on. And the second one, which is from mechanisms to phenomena in itself. And I'm going to start giving you some examples of the bottom one. So probably one of the first models that came out recently, it's my fault that came out. And it's a generalization of a very simple model of infection. I use sneeze on someone with a certain probability, they get the disease, and then they become susceptible again. So they're healed with another probability in the 9 following steps. What you can actually add is the possibility of having interactions between the group. So you need exactly 2 nodes that are infected within a triangle, within a 2 simplex, to infect the third one, and so on. And it turns out that even just adding this little rule creates nonlinearities that lead to bistability in the system and all sorts of rich phenomenologies that don't emerge in the classical linear systems. For example, if you relax your assumptions about this being a simplicial complex, but you actually just work on a hypergraph and you have some sort of nonlinear kernel of infection, you can find all sorts of beautiful behavior. For example, what used to be first order transition, a bistability, as you see on the left, becomes mirrored. And so you have some sort of localization of the infections, which really would mean in this case that most of the network of your system is actually healthy, but you have a core of infected nodes that live, in this case, in the high, in large side simplices or hyperedges, depending on how you. And this kind of sort of new rich dynamics can be generalized. We are finding them everywhere. For example, in models of synchronization, Kuramoto models, right? You can generalize them and go from having nodes that interact on oscillators that live on nodes and interact through edges or to triangles, to actually what have been called simplicial oscillators. They live on 1 simplices, 2 simplices, and so on, and they interact through effectively boundary operators coupled with the differences between the phases. And you have all sorts of beautiful new phenomenologies that appear, traveling waves, oscillating parts of the system that coexist with congealed and frozen parts of the other system, even negative and anti-synchronization, which is actually very, very, very hard to find in Kuramoto models in general. And then if you want going further down, you can actually think about, there is also some evidence that this kind of higher order effects change the way we coordinate and evolve, for example, norms within a system. What word we use to call a color, it changes the way in which we can, for example, the minimum number of zealots or militants that can only use one word, that you need to flip a social system. Okay, so these are all examples of what's going on here. On the other side, there has been a lot of work that, as I was saying, started before trying to go from the data and extract information. And I'm here, it's going to be, again, a little bit self-referential. There is some work that goes back to at least, 2014, but even some work by Chung and Lee before, using ideas and tools from topological data analysis at the level of fMRI to, for example, compare and show differences between people that have received a substance and versus people that have received a placebo. And more recently, we also have showed that you can use the same topological information to fingerprint different people. So there exists a topological fingerprint of your brain activity that is different between people, and you can use it to actually tell people apart. At the macro level, and also at the micro level, you have evidence from work done on hippocampal cells, grid cells, and so on, that there is a topological encoding of the world that is there. So we have evidence at the macro scale, at the micro scale, and as I was saying earlier, there is also evidence not for topological effects, but for informational effects, higher order informational effects, coming from how we integrate information, for example, between sensory areas and cognitive areas, what would be associative areas, and so on. Okay, so there is a lot of evidence that this higher order mechanism, these higher order observables, or at least what we can take out from data without a model to interpret them, exist, are there, and we haven't really linked them together. Very recently, an idea came out, which is that complex systems in general, which really are just large systems that are interacting, might really have an underlying low rank structure. This is a Nature Physics that came out last year, and effectively what you can do is you take a network, any network, and you can show that in most cases the effective rank of this network is much smaller with respect to the size of the network. Why is that important? That is important because if you actually work this through, you realize that if such a low rank, low dimensional manifold of the dynamic exists, what you are doing, you're effectively inducing higher order interactions. So you wouldn't be measuring higher order interactions from the dynamical properties of the system. And because what you're doing is that you're going from the network to the dynamical fields, then you reduce it, and then you have this kind of emerging higher order interactions. And the question then becomes, okay, in some cases, I can have mechanistic higher order interactions. In other cases, I might not have them. I might have only emergent ones. How do I know? How do I tell them apart? Okay. So in a sense is, given that I might know a mechanism that tells me how I go from one configuration to the next configuration of the system, and I have some behavior that I explore, or that I measure, how do I go from the mechanisms to the behavior? And this, in a sense, it's slightly faster, slightly easier, right? Because you can write down the equation, and in worst case, you simulate. And more, and also more importantly, if you want, is how do I go back? How do I, given a certain set of observables that I have, what is the limits? What are the limits within which I can reconstruct the mechanism back? Now, this is particularly hard, as I was saying, when we allow for higher order interactions, higher order terms in our model. Why? Well, because in a beautiful world, we would have on the left, dynamic mechanisms, dynamical models that are neatly divided in higher order and low order. And on the other side, we would have low order observables, neatly, let's say, divided in higher order observables, for example, every homology above 1, and low order observables, anything which you would just measure on the nodes, how many infected nodes you have, pairwise correlations, and so on. And if everything was, good and right in the world, they would map 1 to 1. However, we do know that that is not true, because low order models can have non-trivial higher order observables, values of this, and vice versa. So you can imagine that when we go back, then it becomes a mess. Now, within this context, what can we do, and what do we lack, and what we can do? Many things, and I'm going to give you a very non-exhaustive list. So the first one I would say is what I call the slightly less hard problem. And by that, I mean a systematic study of the link between some mechanisms, at least the ones that we know very well, the canonical ones, and their behavior, especially their higher order behavior. Then we also need to ask the question, at what level can this reconstruction be possible? Now, it is possible that some of the information can be reconstructed. You could measure your whole fMRI, you can reconstruct the activity, the interactions at the at some regional level, but not all the way down to the voxel level and so on. And I'll try to show you that, convince you that some of the tools that we're building, in particular what I'm calling higher order renormalization flow, is important. And of course, all of these should basically feed into the future steps, which is linking this kind of multi-scale description of activity to the underlying dynamics. And of course, figuring out what happens when you have more refined higher order correlations, as I said. For example, what do I mean by that? When you have a social system, you might have many groups, that are interacting, but you might have these groups distributed on the population, or they might be nested one inside each other, and that changes the dynamics that emerges. We know that, for example, from ecological systems. Okay. What I'm going to be talking about is two papers that approach the first two, because I don't know yet how to do the third. I hope someone will eventually solve it for me. I hope you still see, because I destroyed my screen. Okay, good. Let's start. What do I mean by slightly less hard task? The hard task would be start from the signals and reconstruct the underlying structure. The slightly less hard is flip this around. So choose some mechanism, produce the outcoming signals, so time series in this case, and so basically pick a mechanism and then study systematically what are the higher order behaviors and under which lenses we can see them or not. Which mechanisms are we going to look at? Well, the first one is the one that I mentioned at the very beginning, higher order Ising model. So these are spin models in which your spins can be up or down, and then you have an interaction term which can be of any order. Instead of having just two spins, you can have 3, 4, and so on. And we're going to stop at 3 because that's enough for the argument. And then we're also going to be looking at that simplicial contagion model that I showed you earlier, with the one where you have edges and triangles, and then to infect through the triangle, you need 2 nodes to be infected. Okay. What I'm going to be looking at as observable, and here it's a trick, I'm not going to be looking at topological observables, just to show you that actually we have effects in the informational one, from the informational point of view. What we're going to be looking at here is what's called total dynamical O information. Now, let me show you how it's written down. You start from what's called O information, which encodes the balance between redundancy and synergy of a system, of a set of variables. So if it's positive, there is more redundancy in the variables you're looking at. If it's negative, there is more synergy. And those H's that you see there are the entropies of that set of variables. So effectively what you're doing, you're looking at the difference between the entropy of a variable minus the entropy of the set of all the other variables, remove that one, and then you have the total one. We add time, so we actually don't look at the instantaneous entropy of the configuration, so we look at the prediction in the future, in one step in the future, and then we condition on the past to remove possible mixing of information down there. Now, you don't really need to sort of understand all of this, because it's also very badly, the formulas are clear once you look at them, but they're complicated. Just trust me that this is telling us how much information is redundant in the current state of a system to predict the next state of these 3 variables, and how much of that is synergistic. So how much information you can only access when you look at the 3 of them together rather than as the pairs or the individuals. Good. So what are we going to look at? We're going to simulate the systems that I told you, and we're going to look at 3 prototypical situations. One, where I have the simplex, so that I have the mechanistic interaction. 2, when I only have the edges, the 3 edges, the clique, and then the case where I have 3 nodes. Actually, this is not really true. I'm not just looking at 3 disconnected nodes. I'm taking also every possibility in which I have 1 or 2 edges, just not 3, okay? And then I simulate this. And for the Ising model, that's what I find. So from left to right, the higher order effect increases. So the J2, the coupling of the interaction between triplets increases. And then you see that basically this blue bar goes down just for the cliques. And it's telling you, just for the simplices, which is telling you that there is an additional synergistic effect to this, when you actually have those. And the same thing happens much stronger, much more strong way when you're looking at the simplicial contagion. So that system that is actually a diffusive system to some degree, has a much stronger signature. Now, this means that we have higher order signatures of these dynamics, but it doesn't mean that we do not have lower order signature of these dynamics. And can we investigate that? So we do this by choosing 2 different observables, one that is pairwise. So we use pairwise transfer entropy between nodes. And then we use also the dynamical information, the one I just showed you. And then we basically ask how overlapping the distributions are of each of them when we measure them on the simplices or on the cliques. And this is what you get in the case of the Ising system. So basically, for the transfer entropy, the pairwise one, you don't see anything. Instead, for the dynamical information, you see that there is a region of parameters where there is a large difference. And the same thing happens also when you look at the simple short contagion case, right? So, which is really telling you that the mechanistic effect of adding these three-body interactions, in this case, the simplices, can only be picked up by the higher order observable, not by the low order one. To convince you even more, if you do the same game, well, looking at the triplets versus the cliques, so I'm forgetting about the higher body interactions, what we find is that there is a much stronger effect in the low order observable, so in the pairwise one, rather than in the higher order one. Okay, so we're actually losing that part there. And of course, I started telling you this story talking about slightly less task. We can play this game in let's say, to make it simple, we can do the simple version, the simplified version. We assume we know the network, so the pairwise interactions, which is typically the case in real systems. We assume that we have an approximate number of simplices that we know, like we know there is about 100 triangles in my system, maybe from local measurements. And then I can say, well, I'm going to take the first 100, the first top K most synergistic triangles, and then I ask whether I'm doing the reconstruction well. And then you see that for different cases, these on the right are accuracy curves. You see that depending on where you are in this parameter space, in many cases, you can actually do reconstruction very well. Okay. Now, of course, this is not the full problem, right? Because the full problem would be I've got the whole signals and I'm just, fitting some sort of you can imagine Bayesian inference model that fits the whole hypergraph to this. But even just using these very simple methods, you can actually get pretty good results. And interestingly, as I was mentioning earlier, there is a nonlinear dependence in how well you reconstruct, which actually means that there is a nonlinear dependence in how strong the effect of the higher order interaction is within the dynamics, and that can be picked up by this. Okay, so first part is nice. We do have these synergistic signatures that emerge from at least two prototypical higher order mechanisms, which we know also that Kuramoto models are there, but I have not shown you. There is this nonlinear relation between the higher and low order control parameters in terms of their effect on the dynamics. And these higher order signatures tend to be invisible to low order observables, right? And then you can use them for detection. And of course, there is an intricate relation between them, and we haven't really figured it out exactly, but this actually gives hope that an inferential engine might be able to actually reconstruct this. And it gives us regions of the parameter space where we could actually try and see whether we can actually do it there and not encounter the fact that it is impossible simply because there is no structure in the data. Now, what's next? Well, of course, we would like to have analytical descriptions of these. And at least for the easy model, we've done it. It's on the archive. It came out last week. So we can actually, or a couple of weeks ago, so you can take a look at that. And of course, the other part will be to extend it to more processes. All the dynamics I described are discrete dynamics. You are either infected or non-infected. You are either up or down in spin systems. What happens when you do this with Kuramoto models, for example, where you have synchronization and continuous, or even more general dynamical systems? We don't really know yet. The picture seems to be more complicated, but it's a very open question, and it relates to even deeper questions in dynamical systems. And of course, the big problem here is how do we approach all of these when we have no model, right? When we are gonna have, when we have just data. So if you want, the take home here is that we start having one part of the story, but we still miss the second part of the story. So how do we go back? And one step to building the other part of the story, so going back, is to start thinking about what happens on multiple scales. The idea of does information live at every scale? Sorry, does information that live at every scale have the same reconstructive power or predictive power? This relates to ideas of that have lived in the complex systems community for many decades now about emergence. You might have microscopic dynamics that evolves in time, and then you have these macroscopic emergent properties that are causally decoupled from the macroscopic degrees of freedom. And the question is, can I actually maybe only predict and reconstruct the emergent properties or the macroscopic, and to what degree can I do it? So it's a very hard problem. How do we break it down? One way of breaking it down is to try and actually do this rescaling through different scales of the system. Okay? Now, this is something that's called renormalization in physics, typically, and especially in networks, because of their heterogeneity, it's been very hard to do. But recently there has been a proposal which is called Laplacian renormalization group, which is literally based on the idea that you can take a graph, you apply this Laplacian renormalization group, which I'm going to describe in a second, and then you can continue, and this renormalization structure respects the properties of the system. For us, what is interesting, it's interesting that since you're producing a coarse graining at every step of this procedure, you can actually have macro nodes, and you can aggregate the dynamics of the macro nodes and then ask questions about whether there's more information in the macro nodes rather than in the micro nodes. Just to give you a very, 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 very simple example of what happens, imagine to have a network. In this case, this is just a pairwise network, pure graph, where you have a community structure. This is a stochastic block model. We can compute the specific heat of the network. It will make sense in a second. And from there, we can actually predict where we should see effects of the normalization. And in our case, we are in this, what I'm showing you here, which is, again, just a cartoon. I am simulating an Ising model on this graph, and then I am doing majority vote aggregation within the macro nodes. And then I am measuring how much information there is between nodes. So that TDMI stands for time delayed mutual information. The idea is that if I take two nodes in my graph, how much information there is in those two nodes that predicts the state of the system in the next time step for those two nodes. But now the nodes will change depending on the aggregation, right? At the beginning, there will be the original nodes, and then it will be macro nodes, macro nodes, and so on and on and on. And what you can see, for example, if you just do this, is that you have a peak that then stabilizes of this time delayed mutual information. And this peak actually happens exactly where you would imagine that should happen based on the normalization flow, which I'm going to explain in a second, right? So this is an example of emergent dynamics that is not visible at the microscopic level, but it's visible at the right scale, which in this simple case is the scale of communities. And the null model I'm showing you there is the one where instead of doing the aggregation following this magic coarse graining, which I'll describe in a second, you actually just randomize the aggregation. You see that you don't have this effect anymore. Actually, the information goes down a little bit. Okay. So how does this magic, and then we call it emergence if you are statistical mechanicians. Now, this is what I call renormalization. And let me tell you how this relates to higher order normalization. Okay, just for, again, the non-physicists that are out there, these are ideas that come from statistical mechanics with the idea that when you're close to a phase transition, the system becomes scale invariant because the fluctuations percolate throughout the system. So you could actually normalize throughout, sort of renormalize throughout multiple scales, you would always have the same properties throughout the system. The problem here, historically, to do this on networks, it has been that networks don't have a fixed dimension, don't live in 2D or 3D, they're not lattices, but they can have heterogeneous degree distributions. So you wouldn't know how to put together the nodes. Should I put together all the nodes around one node? Should I put together a certain number of, so in boxes of a certain number, and so on and on and on. One answer, which I think is a very good answer, came last year, which is, well, let's use dynamical models. Let's use diffusion to do this. And diffusion, in the simplest form is that equation that you see up there. We imagine a fake diffusion. And so it basically diffuses through the system, okay? And so that L that you see there is the Laplacian of the network, which we can sort of compound into that rho, the solution of that rho of tau, which I'm going to call density matrix. And the idea is that as the process, as this diffusion process continues, it discovers different scales of the system, okay? So you can use this to decide what are the clusters, what are the aggregations that you're going to do. Right? So you go forward, and then everything that is more connected than that has a certain raw ij, so the density matrix on the off diagonal is stronger than on the diagonal, you're going to call that a cluster, and then you aggregate it, and then you continue, okay? I am skipping on the details here because it really doesn't matter how you do this. It's important, you can look at the paper, but the idea is that we're looking at how things diffuse, and then when there is some autocorrelation with the systems, then it's gonna be apparent, and then you can actually use this to renormalize. What is the telltale sign of a system that is scale invariant? A way of looking at it is by using the spectral properties of this of the density matrix that I showed you earlier, which is that function up there. If you're not familiar with it, just trust me. It's related to the spectral dimension of the system. And when you have a scale invariant system, it looks like the one that you see on the left, where there is a plateau. You know that there is there should not be real scale invariance in the system. And so what happens is that if I actually decide to renormalize within the plateau, I'm going to have something that looks the same, okay? Now, there is a problem here, because when we say looks the same, if it's networks, historically, traditionally, we have looked at the degree distribution, right? I show you the picture and you go like, aha, okay. Why? Because they look tree-like, they look like a scale-free network and so on. And actually in the paper, the one that is cited there, that was mostly the argument that we're making. So the degree distribution doesn't really change. But the underlying difference between scale-free networks and scale-invariant systems, which don't need to be networks, is that you have the kind of plateaus in this entropic susceptibility, okay? So that curve that you're seeing there. Now, beautiful. We can do this on graphs. It seems to work. Andrea Gabrielli, Tommaso Gili, some of the authors in the paper have subsequent papers in which they use this for communities and so on. So it works. Now, what about higher order networks? Okay. Now, our elements, as I was said earlier, and are either simplicial complexes or hypergraphs. So it's going to be either simplices or hypergraph or hyperedges. What can we do? Well, the first approach would be forget about it, right? Just use the underlying graph and do it again, right? And let me show you what happens if I do this in the pseudo-fractal simplicial complex, where I'm just taking a triangle, attaching 3 other triangles, and so on, which should be the most scale invariant thing it is, because it's by construction a fractal, okay? If I do this with a higher order, with the Laplacian normalization of the underlying graph, or the one skeleton, if you want, you get something that looks like this, okay? So it really doesn't work, right? You see, even by eye, you see that you're not reconstructing, so the fractal should collapse on itself, right? If you're normalizing properly. Why does it fail? Well, it fails because we need a diffusion process which takes into account the fact that we do have this higher order structure, right? We are gluing triangles on triangles. We're not gluing edges on edges and so on, okay? So what is the right diffusion process that we should look at? Well, the typical diffusion process is between nodes. So you leave on nodes, you jump on an edge, and then you go down on another node, right? But in a higher order system, we can imagine anything, right? So this is the standard one, where we can imagine going from nodes to triangles to nodes, okay? I know this would break, this doesn't work for the Hodge Laplacian, right? But you can write it down, yeah? I'm going to talk about our Hodge Laplacian later. You could imagine sitting on triangles, go through edges to other triangles, right? So eventually, right, instead of having one diffusion process, you have a family of possible diffusing processes, right? And which we call, so these processes, you can imagine, they're indexed by K and M. And to each of these diffusive processes, we can associate an adjacency graph of which simplex of dimension K is adjacent through a simplex of dimension M to another simplex, right? So you start from a higher order, from a simplicial complex, and you go to a graph of this type of adjacencies. You could do this on hypergraphs, it doesn't really matter. And you end up with what we call cross-order Laplacians, because they cross between Laplacians. And each of these operators is, labeled by K and M, which is telling you from where you're starting through what you're going to where you're arriving, okay? And then the scheme is the same, okay? So you start with in this case, it's simplicial complex again, but, it doesn't matter. You find a way to classify. So you diffuse, you choose a certain tau, and then you course grade down. Now, formally, this is done in this way, right? So you start from the diffusion process, you choose a certain scale, you compute it's the density matrix or heat kernel, which is that matrix, and then you identify simplices that have an off-diagonal term that is larger than the diagonal term. Why? Because the idea is that you're more confusable with the other than you're confused with yourself. In diffusion terms, you're diffusing more to the other simplex than to yourself, okay? There is a whole problem about how we choose that tau star, but that's a question for another time, and you can ask me later, well, how we usually go about that. So let's see what happens in the pseudo-fractal. Okay, we do this, we compute all the specific heats curves or entropy susceptibility curves for all of these Laplacians, cross-order Laplacians, and you see that there is one that seems to have a little bit of a plateau, okay? And the reason why it has a plateau with a bunch of little waves is because we are doing this on a small fractal, pseudo-fractal complex, right? So if you made it larger and larger, those things would sort of even out, right? And you see that also, so both the 1, 2, and the 2, 1, which would be edges through triangles or triangles through edges, sort of get you a little bit there, even though the second one is better. But even by eye, you can see, this I showed you before. If I do the renormalization with the graph, Laplacian is wrong. If I do it with the proper one, I get it right, even just by eye, okay? So at least at this level, it works. Does it work if we have simplicial complexes with more complex structure, with more heterogeneous structure? And here I'm using something that's called network geometry with flavor, which is a model that has been proposed by Giannestra Bianconi and collaborators a few years ago. Well, 8 years ago at this point. Wow, time flies, 9 years. Anyway, and the idea here is that you're growing a simplicial complex by attaching randomly one simplex of a certain dimension as you go through, right? And then here you can do it attaching edges, attaching triangles, two simplices, attaching tetrahedron, three simplices, and so on, right? And then you can play the same game. And here it becomes immediately obvious that there is only one curve that is actually giving you a big plateau. And it's always the one that corresponds to the correct attachment kernel, in the sense that to the correct size of the simplices that you're attaching to your system, right? So it's actually picking up something about the underlying structure of the system. And the beautiful thing, as I was telling you earlier, that, why do we say that this is scale invariance? It's because, again, if I do the renormalization with the wrong one, my entropic susceptibility drops when I recompute it on the aggregated, on the renormalized simplicial complex. If I use the right one, you see that it stays much more conserved. So actually, I stay there if I'm doing it right. And this is the real signature of a scale invariant system. Beautiful. Why do I care? Well, I care because we can measure this in data, not just in models. How do we do this? Well, we compute all these curves, as I showed you earlier, and then we came up with a logarithmic version. So basically, it's a measure of how long the plateau is for each of these curves. And so we end up with a little feature space, like a little radar plot for every data set that we can look at. That tells us how, the longer you are, the further from the center you are, the more scale invariant you are under that lens and in that cross-order Laplacian. And the little gray thing you see in the center is the same measurement done on a randomized version of the adjacency graph from which you build the Laplacian, so the simplex adjacency graph. It's randomized not completely, it's a configuration model, so you're keeping the local structure. And then you can do this for many, many, many data sets, right? What you see here, for example, is that even just by eye, there are data sets that come from similar domains, biological, neuronal, and so on. They tend to end up in the same area. This is a low-dimensional projection of the high-dimensional PKM vector, let's say. And more interesting, you actually can see that there are, across the data sets that we looked at least, there are different behaviors. Right? For example, the first one on top left basically has no scale invariance on top of just its local structure. So it's not significantly more scale invariant in any of those dimensions with respect to the null model that we use. But for example, the second one is, and so on and on. So you can actually start looking at these different models depending on what you're interested in and seeing that there is scale invariance. To be honest, I haven't really looked properly at what is scale invariant in Game of Thrones, or Song of Ice and Fire. But it's there. You can the paper is online, so you can actually find the data set there if you're interested. So take home. We generalize this Laplacian renormalization framework to higher order networks, which is a general catch-all term for hypergraphs and anything which is more restrictive, including simplicial complexes. It seems that using these tools, we can fingerprint different networks in different ways. And I would say actually more importantly is that some of the structural properties of the real systems could be hidden if you just take a node-centric perspective, right? So we can only look at what happens around nodes and with nodes, but we actually have to take into account the other things, which I think is the biggest take home. Now, we could and we should improve the scheme, okay? So first of all, we only looked at one KM relation at a time, even though then we put them together, right? It would be easy to sum them in some way or to average them to allow the possibility that maybe it's not really M, it's M between M0 and M1, something of this type, which is more realistic for real world data. And also we should find a way of assessing the quality of the renormalization that we're doing. And this is not just related to that tau star that I was mentioning, but also to something in terms of, we could argue that we could do this normalization under different dynamical processes, for example, right? We could actually use other we could not use the diffusion, we could use synchronization and so on. And so we need a way to be able to say, well, when I compare, you know, the renormalization that I'm doing with a Laplacian from diffusion in all these dimensions and the one I'm doing the synchronization, how am I doing? And here it's actually some work that we're doing right now. So the pictures are going to be very ugly, but just to give you a feeling of what it means. So this is the pseudo fractal, the same one I showed you earlier, that is renormalized. Here we're not renormalizing, we're just doing the clustering of the edges of the simplicities in this case, using the Hodge Laplacian. So the actual proper Hodge Laplacian that you would use on a simplicial complex. And the first thing that you see is that the colors, especially at the beginning, they're all over the place, right? They're mixed. So it doesn't seem, you have some classes that are non-local. So you have some green here that goes green here and so on. And then as you proceed, it gets a little bit more like something you would imagine from a diffusion process, but you still have this core that instead of like going out, it lives here. And then in the end, it ends up here. And why is that the case? Well, because the Hodge Laplacian, it's not a diffusive Laplacian, right? It's a reaction diffusion Laplacian. Actually, you can write down the Hodge Laplacian as a sum of what's called the Bochner Laplacian, which is a sign graph, has a bunch of properties, but it is a graph-like Laplacian. So it gives you a diffusive behavior plus the formal curvature. And this is actually a forcing behavior, a forcing term in your equations, right? So you're not really diffusing anymore. And that's why here you end up with some weird effects because things are bouncing off the edges, coming back and so on, okay? And this is the idea. How do we then compare? How can we compare then, you know, diffusion and renormalization schemes that come out from using the Hodge Laplacian, Bochner Laplacian, cross-order Laplacian that I described earlier, and so on? We don't have a full answer, but we think that one way of looking at this is in terms of harmonic morphisms. So we can actually define, you reuse ideas from harmonic morphisms to basically compute something that we're calling a harmonic degree. So if you have a harmonic morphism, the size of the counter image has to be constant for all the points that you're pulling back. Okay. What we can actually do is that since our renormalizations are maps that, you know, basically compress things in going ahead, we can go back and look how locally harmonic the structure is. And then, for example, here you can see that if we do this on a Barabasi-Albert network, and here you can't really see it, but by using the L0, the graph Laplacian spectral dimension, but if you look at the harmonic degree, we are doing perfectly well using the Laplacian graph renormalization. While if instead, if we do it on the pseudo-fractal, and we use the Hodge Laplacian, the Bochner, or the cross-order Laplacian, first of all, you have different, let's say, violation of this harmonic degree. But in particular, they are not always perfect. So it's actually telling us that the renormalization that we are making is breaking locally sound structure. Now, exactly what it means, we don't know. And whether it has impact on the dynamics, I assume so. But we have ideas because, you know, if you go from harmonic morphisms to horizontal conformality, you can actually link this to a dynamical interpretation of these in terms of random walks. And the idea would be that you have perfect harmonic, you know, one harmonic degree, so perfect harmonic morphism when the random walks that are living on your micro scale are conserved functionally at the renormalized scale and so on and on. So it would be a proper mapping of scales the same way it would be in physics. Okay, so with that, of course, all of these, then the question is beautiful. We have a bunch of tools. We still need to do a few things, but then how can we use this downstream to understand emergence, as I was saying earlier, but also mixing processes, right? Because now I just mentioned that we have a dynamic, or at least we think we can relate this to a dynamical interpretation of this renormalization and how it biases a random walk defined at every scale of the system. With that, before I thank you for your attention, let me do a little bit of shameless commercial here, which is, first of all, there is a Marie Curie doctoral network that just started. Fortunately, we already recruited everybody, but the website is going to be full of good resources about all the things that I spoke about today, from the theoretical part, dynamical systems and topology and information theory, through data, so how we actually look at this data, and computational approaches to this. Next, there is a school, if you're interested in all of this, that is going to take place in Sicily next summer. And those are some of the speakers, and you see it's quite mixed. We have Karina Curto from topological side, we have Laplacian Bic and Ana Paula Millan from dynamical systems, and so in Sebastiano Stramaglia for the information theoretic, Mario Lingatica for the neuroscience. So it's actually going to cover a bunch of these things. And if instead you are already working on these things, do send us something for TopoNets, which is one of the longest running satellites at NetSci. It's going to take place in Maastricht next summer. And finally, I am hiring. There is a ERC grant that is starting soon. We're going to have a PhD position soon, open a postdoc position open in the next few months, probably 5 to 6 or something like that. And then for more positions coming out in the next couple of years. So talk to me, look at me, look for me online. You're going to find it there. And with that, let me show you the faces of the people responsible for all the work that I've done here. And here you can find the papers with all the details that I skipped over during the talk. Thank you.
Thank you very much for the wonderful and beautifully done talk, I have to say. The visuals are amazing. Before we go to questions, I would like to ask everybody in the audience to unmute themselves and give a round of applause for the speaker.
Wow. First time that I see that happening online. Thank you.
Yeah, unfortunately, it does not work. Like, you cannot hear everybody clapping, but well. All right, then let's go to questions. So if you have a question, please just unmute yourselves and go ahead and ask the question or post it in the chat.
I destroyed everybody. Okay.
Oh, that's a good question. So this renormalization on fractals, right? I mean, fractals are self-similar at different scales. So you expect it to sort of zooming in doesn't change the fractal. So then on real data, there's sort of a range in which you expect to have this self-similarity sometimes.
Yeah, that's actually what you see here, right? For example, even in this case here, right? If you were in an infinite system, you just go up and then stay flat and go forever. But since this is a finite size system, it's going to go down. And that's actually what typically happens when you have scales. For example, in the example that I gave you about the simple one, the one on graphs, let me just find it, the one where we have the communities. So in this case here, the fact that you're seeing, so this first peak here is really corresponding to the fact that you're starting to see the communities. And that's why, we expect, something around here to be where the information integration happens, is because you have seen the communities, you're starting to see the links between the communities. That's when it happens. And this is really just the fact that there was a little bit of asymmetry in the system. So there is actually a second block to communities. And something like this, it's what people are using to do community detection, right? To say, okay, there is this scale, there is this scale, and so on. And
so those are scales at which you expect to find communities.
And by converse, when you have something flat or something that keeps going up and keeps going down, then you know that there is something that is either invariant in this, if it's flat, or it's a scale that is progressively more structured or less structured, and so on. So that's the way you read plots in this sense.
I see. Thank you.
No problem. We have video people.
Yeah, who's next? Yuri, go ahead.
Can't hear you, Yuri. Sorry.
You are unmuted, but it doesn't seem like.
Okay. Now I have the microphone. Do you hear me?
Yeah, I do.
This way of doing renormalization is susceptible to noise. So, for example, if I perturbate a little bit the network, the final result changes a lot, or?
Well, yes and no, in a sense that of course it is, right? Because you're going to see it. But for example, let me show you this example here where you look at, no, this is wrong. The one with the pseudofractal, let me find it. Here, when you have, no, what is it? Give me a second. Here, okay. So here, it is susceptible in the sense that, for example, depending on how you decide whether this is a plateau or not, you might find different answers here, right? But this is because the system is extremely small. If you scale this up even to a few hundred simplices, this becomes very flat, like the other examples that I showed you. So it is sensible to these small effects. It is not particularly sensible to noise. I mean, of course, it's gonna see the structure. So, but if you just remove some edges and you have other paths, it's not gonna change this in a radical way. Of course, if you have, imagine like a disk and you put a hole in the middle, then that might change it radical, but it should, right? Because at that point, the way you can explore the system changes a lot. So these things, so diffusion, because of it's a diffusive process, right? It doesn't really, if you miss a few edges, if you increase some weights and decreases, it shouldn't change very much. It doesn't change very much. I don't know if people actually have looked at how robust this is, but probably if you want to look for that, you can look at stability of eigenvalue, the first of the spectral gap with respect to small perturbations of a system. And I know there are results there. So in that sense, yes. If you change the shape of your graph or of your complex and so on, then it should change quite a bit. And originally we didn't start with this construction. We started with the Hodge Laplacian, right? Because it's a natural one, of course. But the Hodge Laplacian, apart, before we realized that, we thought that yes, it's actually a reaction diffusion process, not a diffusion process. Gives you other would give you other problems, but also other boons, because since if you think about this diffusion, eventually goes to the zero eigenvector. Just only the smallest one survives, and you have the zeros. In graphs, the zero is the full graph; it's a constant eigenvector. But in symmetrical complexes, it should give you something that is around the holes in the right dimensions, and we're actually hoping for that. The problem is that because of this other curvature term, you don't really get it, and now we're playing with ways of doing the same game with the Bochner in a way. You can do it. You just plug it into the exponential and you do it, right? But to understand what it's doing, to see whether you can actually use that to sort of do this. And at that point, once we know, we can actually start asking questions similar to the one you said, which is how much noise do I need to put in to, for example, forget that I have some holes in a torus, for example, right? And internal development. So, yeah.
Okay, thank you.
Okay, are there any more questions from the audience? Okay, I have a couple.
Sure.
Like one of the first things I wondered actually when you started talking about this fractal, there is like something called discrete Morse theory, which is somehow it's a theory of flows on things like that, like simplicial complexes and so on. And also when you were talking about this clustering, it somehow reminded me of like one could maybe, and this probably has been done, like clustering of simplicial complexes using some flows. Do you know about this? Or
no, I know about this. We thought about this in another context many years ago, because we were trying to do skeletonization in a nice way on simplicial complexes. I haven't really thought about this back in this context, but of course it would make sense. I don't have a ready answer in terms of saying yes, it sounds like a good idea, and I think it would be worth trying to see whether we can relate that, probably through the lens of the harmonic morphisms I was saying earlier. So I was mentioning earlier, because they give you a bit more of a combinatorial structure they can look at, rather than this because when you do it with diffusion, this is a continuous process, right? So you actually have other problems like how do I choose where I cut, right? And which is, again, not really a problem because you always cut when it's going up, right? So if you do it around there, you get the same thing typically. But yeah, no, there are no proofs of this. This comes from the statistical mechanics literature. And the interest here is to see how dynamical system, let's say, how scale invariant a system is as you change the scales, and it has been repurposed to become a lens of where is the important structure in heterogeneous complex systems, and we're just scratching the surface in that sense. So I don't really know where to point you to someone who has tried to put the two together, but that could be actually a good. I mean, if you want to think about that, let me know. I'll be very interested in. Yeah.
Okay, I'll see if I can if I can find some time. I think it's very, very interesting. There is like Uli Bauer's group. I don't know if you know Uli Bauer. He's in.
I know Uli, yeah.
Okay, so like I have a feeling that like he works a lot on these things. So maybe. Yeah.
Should try to really.
If I talk to him or some of his students, I can point them to you.
Okay.
Okay. I had another question regarding the dual, because one could also consider, like, if you consider simplicial complex, you could consider a dual, and then you could run kind of the processes that you do on both structures. Do you think this would add any information? Because I mean, you were saying that the most interesting information is on this like C2 C21, I guess, in the big, or C12. Like you always consider like these highest order interactions.
Yeah.
And that would somehow correspond to the lowest order interaction, or is it just completely wrong way to think about it?
It's a good question. I don't know if it's just the same information. So if it's just doubling information, there is more. Because when you run because you say you'd run this on the dual and then you look at the higher order one. I did not think about this. My feeling is that it becomes, okay, then you have to think about how the adjacency changes, right? Because here everything is defined using the adjacency, which is not the standard one, is the one km, so it actually could be different. So if you do this with k plus 1, so the way that would be respecting of the typical adjacencies in the boundary operator, or Dirac operator, if you want to follow Bianconi, then I think you can actually do it on the dual. And my feeling is that you might not have, I mean, you can do it. I don't know if you get more information. That I have to think about that. If you don't do that, I don't even know how to do it, because how do you map what is the dual in that case, right? Because what is the dual of a hypergraph in a sense in this case? Sure, someone has a definition. Not sure what it would mean in practice here, but definitely, I mean, yes, definitely something to try. Probably even easy to try and to have a first feel about whether it gives you extra information or not.
Yeah. That's what I was thinking, that this is probably something like easy to try out, but good knows if it's useful.
To be honest, before trying that, I would look at what happens when you relax the definition a bit, and instead of having just km is k with some range of m's and so on. Because in real system, you might have a group of 30 people, which is your 30-dimensional simplicity. And then you might have interactions that are 15, 14, 16, and they should all be counted effectively the same, right? And here we do it, but in an artificial way, because you could do all of them differently. But then you end up with very sparse and very disconnected graphs, right? That's the other problem if you don't allow a little bit of flexibility there. So yeah.
Okay, thank you. Are there any more questions?
Okay, good. Then thank you very much again for the invitation. I'm happy to share the slides if anybody wants. So hey, ciao Massimo. All the QR codes are there.
Thank you very much.
Bye-bye.